is a podcast to explain how to make an electric field map. First, a little introduction and some of the quantities related to electric fields. Electric fields are between objects that have charge. And if we think about the inside of an atom, and this is an artist's interpretation of the simple model of an atom, the atom has protons and neutrons in the nucleus and electrons around in the orbitals around the atom. These are the masses of the protons, the neutrons, and the electrons. And you can see by order of magnitude that the proton and the neutron have a very similar mass. Proton is 1.673 times 10 to the minus 27. Neutron is 1.675 times 10 to the negative 27. So almost identical masses, especially when you consider it's times 10 to the negative 27. Very small difference. And an electron is 9.11 times 10 to the 31 kilograms. Both a proton and an electron have the same magnitude of charge, which means the same size of charge, and that is 1.6 times 10 to the negative 19 coulombs. Coulombs is the unit of charge. And to calculate the force between objects with charge, we use Coulomb's law, which is force, which is a vector, equals k q1 q2 over r squared, and k is Coulomb's law's constant, which the magnitude is 9 times 10 to the 9th, and the units, and I'm looking at the formula to come up with the units, so if I rearrange the formula so everything is on this side of the formula, I get f r squared divided by q1 q2. So the units of k are newtons for force, meter squared for r, over coulomb squared per charge squared, because there's two charges there. And then the direction of the force vector is gotten from the r. Now if we think of a simpler way to figure out the direction of f, think about what signs will also be in the equation, or really what f stands for. So if we have a positive charge and another positive charge, the sign for f, the magnitude of f, will be positive. Because a positive times a positive is a positive. If we have a positive and a negative, positive times a negative is a negative, so it will be a negative. If I have a negative and a positive, that will give me a negative. So this is Q, and this is Q, and this is F. And a negative times a negative will give me a positive. The same charges multiplied together will give me a positive. So same sign charges repel, and opposite sign charges attract. And this one also attracts. So just looking at the signs of these, not even paying attention to the r vector, that will tell me whether the force is going to repel or attract, depending on the signs of the charges. Now we are going to draw electric field lines rather than electric force vectors, which is a little bit different. Our formula is F over Q. If you remember the formula for F, that is K Q1 Q2 over R squared over Q. And remember, when you multiply fractions, you invert and multiply. So this reduces to K Q over R squared. So we will be looking at K, which again is 9 times 10 to the 9th newtons, meter squared, divided by coulomb squared. The size of the charge and the distance between them squared. And there are a couple of rules when we're drawing electric field lines to represent the total electric field. First, we draw the electric field vectors, and the electric field vectors are tangent to the field lines. So each time a field line is going to go past an electric field vector, just make sure that it's tangent. We will have just a few electric field vectors to use to determine the direction of our field lines. So we'll have to just use a little bit of data to figure out the shape of the electric field lines. The lines always go from positive to negative. They can't cross because that means there would be two tangents at the same point for the same line, and geometrically speaking, that's not possible. And the density of field lines indicates the strength of the field. So let's just look at two simple examples. We have a single positive charge. So a single positive charge with nothing else in space, we always start with simple situations in physics, is all the lines going radially outward from the charge. If we add a second charge to space, then as much as they can, they go radially outward in space. But when it's coming closer to the other charge, it's going to curve up and away, and then up and down here, and then up and down here. And right in the direct center, you will have an electric field vector from this charge pointing this way, and an electric field vector, use a different, use green, an electric field vector from this charge pointing this way, that is the same size. I use congruency lines to show that, but opposite directions. So just to use simple numbers to model it, if this is -5 and this is +5, adding those two as vectors, we get 0 right in the middle between those 2 points. So right down here, there'll be a little bit of vector, or a little bit of electric field. Here there'll be a little everywhere else, but directly in the center between the two charges will be a net electric field 0. And just to show you a couple of other visuals, here on this top diagram, there are a whole bunch of different electric field vectors generated that will show you the size and direction of the field at different points. And remember, it's the size of the field at the origin of the arrow. So this arrow starts here and goes in this direction. It's not the electric field here at the tip, it's the electric field here at the tail of the vector. So you can see they go up and away and kind of from one to the other going around here. And the lines, you draw them just as lines, will be tangent to all of these vectors. So here we have a whole bunch of data to form, and you can just see how the arrows kind of flow into each other when you have that many data points. Or a nice three-dimensional view is here are two opposite charges, and the field lines flow from one into the other. And when we have equal magnitude opposite charges like that, we call those electric dipoles. This is also to remind you that these are all three-dimensional circumstances, not just two-dimensional slices like we often think of them. Here we have another one where there are two same size charges. You can see they're repelling, or same sign charges, but they are a little bit different in size. This one's a little bit stronger than this one because you can see this one pushes a little bit more. It's a little further out before they start to bend. And then the last piece we add in after electric field lines is equipotential surfaces, and those will go around perpendicular to the field lines because what those represent is an area of equal potential energy. So here is a visual of the equipotential, move my recording thing out of the way, equipotential surfaces around those charges. So circle, 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 and then here you can see it's a big oval once it gets a little bit farther away and around those. And just to see a few more examples like this, here's three charges, and then there you can see them from here. And remember, without even seeing whether they're positive or negative charges from the picture, we can look at them and visually tell that they're repelling in the middle. That means they're the same sign of charge. And then here's 4 charges, and there are the equipotential surfaces for 4 charges. So just to recap, this is showing you examples of electric field lines, the white part, and equipotential surfaces, the red part. In the next section of the podcast, we're going to calculate the values of the electric field, then use those electric field vectors to sketch the electric field lines, and then also to add in equipotential surfaces.